Good day, dear friends. My name is Evgeny Proskrin. I'm the founder of ATF Group. This is an engineering and manufacturing group of companies that started in a garage, producing hardware for transformers. And now it offers digital solutions for a wide range of industrial sectors. Today we are launching a series of micro lessons to share practical knowledge and help our energy sector operate more reliably, efficiently, and safely. After all, our mission is simple: your energy under our protection. In the previous video, we discussed transient processes and methods to dampen them. Today, we begin a new module, one that focuses on a key topic in transformer design: energy losses. We'll trace how attitudes toward losses have changed over time, why the economic factor became dominant, and how the concept of loss capitalization emerged. This episode is introductory and sets the foundation for the entire series. Let's begin with the historical context. Until the 1960s, transformer design was based on two priorities: compact size and low upfront cost. Energy losses were considered secondary. But in the 1970s, things changed dramatically. Electricity prices rose, and even small losses started to carry significant financial impact over time. This gave rise to a new economic concept: loss capitalization, meaning the monetary value of energy losses over the entire lifetime of the transformer. For example, by the early 1980s in the U.S., engineers began factoring in the cost of losses at a rate of up to $3,000 per kilowatt of lost energy. This changed the logic of design itself. Another example. In the 1970s, a cheap transformer with high losses might have been acceptable. Today, such a product would be rejected at the tender stage due to excessive long-term costs. So what is loss capitalization in practical terms? Transformer losses fall into two categories. No load losses. These are constant and occur even when the transformer is idle. Load losses. These depend on the current during operation. Each loss type is assigned a capitalization rate. For no load losses, a coefficient known as KY. For load losses, a different one, KX. The capitalization is calculated as losses in kilowatts multiplied by the respective coefficient in currency per kilowatt. For instance, if KRY is 2,670 rubles per kilowatt and the no-load loss is 6 kilowatts, then the capitalized value of those losses over the service life would be 16,020 rubles. This shift in thinking led to changes in material selection. The core, the main source of no-load losses, began using cold-rolled, grain-oriented steel. Over 30 years, improvements in steel quality have reduced losses by a factor of 2 to 2.5. Given high capitalization values, such upgrades pay off quickly. Design priorities also shifted. Previously, cost reduction and lightweight construction were the goals. Now, the focus is on higher efficiency and minimizing total cost of ownership. For example, a transformer with 10 kilowatts of losses and a low purchase price might lose out to a more expensive one with only 5 kilowatts of losses, because the savings in operating costs outweigh the higher initial price. This shift was reinforced by international practices. In countries with high electricity prices, like the UK, where the capitalization rate may exceed 4,600 rubles per kilowatt, transformers are designed from the outset with loss reduction as a top priority. In Russia, the rate is currently lower, around 2,670 rubles, but it's expected to rise, making the topic increasingly relevant. Since the 1980s, transformer procurement has changed. Buyers consider not just the unit price, but also the cost of energy losses over a 25-year life cycle. A transformer that fails to meet economic criteria may be rejected, even if it meets technical specifications. Now, for a practical exercise, you are a design engineer in 1985. You have two transformer options. Option A costs 80,000 rubles and has 7 kilowatts of no-load loss. Option B costs 92,000 rubles and has 3.5 kilowatts of no-load loss. With a capitalization rate of 2,670 rubles per kilowatt and a 25-year service life, calculate the capitalized losses for each option, the total cost purchase price plus losses. Which option is more cost-effective in the long run? Bonus question. Imagine that 10 years later, electricity costs have doubled. The capitalization rate rises to 5,340 rubles per kilowatt. How does this affect your calculation? How much more favorable does option B become under these inflationary conditions? Today you've learned how transformer design philosophy changed due to the rising cost of energy losses, what loss capitalization is and how it influences materials and engineering choices, why economic evaluation has become the most critical factor in transformer selection. In the next video, we'll take a detailed look at loss types, where energy is lost, the difference between no load and load losses, and what engineering strategies help minimize them. This will give us a solid foundation for managing losses from the circuit design stage. Want to explore the topic in more depth? Visit our website. The link is in the description. Interested in real-world solutions and industry challenges on this topic? Contact us. Our details are on the screen. Want to become a part of the global energy flow? Reach out to us. You'll find our contacts on the screen.